Welcome to the video lecture series Microprocessor and Microcontroller. Paper code is AC502. My name is Dr. Anilesh Day, Associate Professor, Department of Electronics and Communication Engineering, Narula Institute of Technology. This is lecture 26. In the previous lecture, I explained the programming of 8086 microprocessor. After that, I explained the introduction of the memory interfacing, that is, interfacing with the memory with 8086 microprocessor. There, I also explained the concept of the memory banking. In this today's lecture, first I explain the interrupt of 8086 microprocessor. After that, I explain the memory interfacing rest of the part with the help of a typical problem. First is the 8086 microprocessor interrupt and interrupt request. Sometimes it is necessary to have the computer automatically execute one of the collection of the special routines whenever certain condition exist within a program or in the microcomputer system. For an example, it is necessary that microcomputer systems should give response to devices such as keyboard, sensor, and other components when they request to service. The common method for servicing such devices are: number one is the polling method, number two is the interrupt method. So I explain the two methods one by one. First, I explain the polling method. In this method, the processor must test each device in sequence and in effect ask each one if it needs communication with the processor. Number two is that it is easy to see that large portion of the main program is looping through this continuous polling cycle. Such a method would have a serious and decrementing effort on the system throughput. The next method is the interrupt method. Another method would be one that allows the microprocessor to execute its main program and only stop to service the peripheral device when it is told to do so by the device itself. This method, the processor would provide the external asynchronous input that would inform the processor and that it should complete whatever instruction that currently being executed and fetch a new routine that will service the requesting device. Once this servicing is completed, the processor would resume exactly where it left off. This method is called the interrupt method. So what is the main thing? I just explain this thing once again, that after execution of the each and every instruction, microprocessor checks that an external asynchronous input is coming to the processor or not. If not, go to the next line. If yes, it complete whatever the instruction is currently being executed, that instruction, and after that it jumps from this location to the location dedicated for that input, perform the task over there, and then return back to the main program, and then again the execution started. When microprocessor is interrupted, it stops execution the current program and call the special routine which serves the interrupt. What I explained. It is very important. The event caused by interruption is called the interrupt, and special routine executed to service the interrupt is called the interrupt service routine. So cause of the interruption is interrupt, and where the special routine where you execute the service of that interrupt is called the ISR or interrupt service routine. This method increases the system throughput. And 8086 interrupt sources. This is the external source signal, and 8086 can interrupt from the external signal applied to the non-maskable interrupt input pin or the interrupt input pin. So these are the pin available in the chip. So these are nothing but the hardware interrupt. Special instruction. An execution of the interrupt instruction INT. This referred as in software interrupt. So here the interrupt may be classified into two different categories. One is the hardware interrupt and one is the software interrupt. Condition produced by the instruction. And 8086 interrupted by some condition produced in the program by the execution of an instruction. For an example, if you divide it by 0, the program execution will automatically be interrupted if you attempt to divide an operand by 0. Next one is that interrupt sequence of 8086 microprocessor. This is a very, very important one. First one, that it decrements the stack pointer by 2 and pushes the flag register on the stack. So what will happen? It starts to locate the memory location which is dedicated for the stack using the stack pointer, and stack pointer decremented by 2, and what is the content of the flag register, that is pushes on the stack. Next one is that it disables the 8086 interrupt by clearing the interrupt flag IF in the flag register. So it's clear the IF flag. It is another important one. Third one is that it reset the trap flag TF of the flag register. So in the 8086, the flag register is take the very important role for the interrupt sequences. Next one is that it decrements the stack pointer by 2 and pushes current code segment register on the stack. That means whatever the stack pointer located, the location decremented by the 2 and current code segment register content on the stack. What is the code segment register content, that is also pushes into the stack. It does an indirect for jump to start the procedure by loading the CS and IP values to start of the interrupt service routine, because CS and IP value, the combination of these will generate the 20-bit physical address, and from that particular location address the interrupt service routine starts. Now I will explain with the help of the diagram. Now this is the mainline program. That means the execution of the program is going on. Then microprocessor find the any external asynchronous input comes through the processor. Now first is that it push flags clear IF, clear trap flag TF, TF interrupt flag, clear trap flag, push CS, push IP, fetch the ISR address. After fetching the ISR address, it jumps from here to the interrupt service procedure routine. So what will happen? In there, the inference service routine is written. Then after that, the IREAD instruction, that is it pops the register before returning from the stack to the main program location. Pop IP, pop CS, pop the value. Pop means it's retrieve the value from the stack, and after that it's come to the main program, and from the main program the execution is going on. So this whatever I explain, I just explain same thing in the next slide. The 8086 gets the new value of the CS and IP register from the 4 memory addresses. Next one is that when it responds to an interrupt, the 8086 goes to the memory location to get the CS and IP values to start the interrupt service routine. This thing I explained in the previous slide. And 8086 system, the first 1 KB memory from 00000H, that means 50H, it is the beginning of the memory, and to 003FFH is reserved for storing the starting address of the interrupt service routine. So this is the 1 KB location is reserved for storing the starting address of the interrupt service routine. Next one. The block of memory often called the interrupt vector table or interrupt pointer table. It is very, very important part. It is written in the table which is known as the interrupt vector table or interrupt pointer table. Since 4 bytes are required to store the CS and IP values for each interrupt service procedure, the table can hold the starting address for the 256 interrupt service routines. So these are the interrupt sequence of 8086 microprocessor. The next one, I'll explain the interrupt vector table of 8086 microprocessor. So this is the diagram of the 8086 interrupt vector table. And from the table, we can find it out there is a different type of interrupt written. So it is an interrupt may be classified into different types. Type 0 pointer, that is a divide pointer. Type 1 pointer, single step. Type 2 non-maskable. Type 3, type 4, type 5, which I explain in the next slide. Now what will happen? It is a CS bit address and IP offset locate the location. So from this location 0000008 to 014H, it is dedicated for the interrupt pointers 5. From there to 07FH, it is the reserved interrupt pointers 27. And from 080 to 3FFH is for the available for the interrupt pointers 224. So why it's called the vector table? Because this table give you the direction where you want to jump. That's why it is known as a vector table. Now I'll explain the 8086 interrupt types, which I already shown in the last slide. First is the type 0 interrupt. It is commonly known as a divide by 0 interrupt. When the quotient from either a div or idif instruction is too large to fit in the result register, 8086 automatically execute the type 0 interrupt. So this is the divided by 0 or type 0 interrupt. Next one is for the single step interrupt or type 1 interrupt. The type 1 interrupt is the single step trap. In the single step mode, system will execute one instruction and wait for the further direction from the user. That means you can go one step, you can check that step, and then you can execute that step. That's why it is called the single step mode. That means you check each and every step after execution, before execution. The user can examine the content of the register and memory location, and if they are correct, user can tell the system to execute the next location. The feature is useful for the debugging the assembly language program. So this is all about the single step interrupt or type 1 interrupt. Now I explain the type 2 interrupt, and which is commonly known as a non-maskable interrupt. Non-maskable. I explained the concept of the maskable and non-maskable already in the 8085. So I'm not giving the concept of the what is maskable and non-maskable. As the name suggests, the interrupt cannot be disabled by any software instruction. This interrupt is activated by low to high transition of 8086 NMI input pin. In response, 8086 do a type 2 interrupt. So type 2 interrupt is commonly known as a non-maskable interrupt. Now go for the type 3, which is known as a breakpoint interrupt. The type 3 interrupt is used to implement the breakpoint function in the system. The type 3 interrupt is produced by execution of INT3 instruction. Breakpoint functions is often used as a debugging aids in case of the single stepping provided the more details than wanted. So this is all about the type 3. Now I explain last one is a type 4 interrupt, that is called the overflow interrupt. This type 4 interrupt is used to check the overflow condition after any signed arithmetic operation in the system. If the 8086 overflow flag wave will be represented in the destination register or memory location. So these are the type 0 to type 4 interrupt I explained in this site. Now next one is the software interrupt or type 0 to 255 interrupts. The 8086 INT instruction can be used to cause 8086 to do one of the 256 possible interrupt types. The interrupt type is specified by the number as the part of the instruction. User can use an INT2 instruction to send execution to NMI interrupt service routine. This allows you to test the NMI routine without needing to apply an external signal to the NMI inputs of 8086. So this is for the software interrupts. Now next slide I'll explain what is the difference between the NMI and INTR. First I'll explain what is the NMI and what is the characteristics of the NMI. After that I'll explain what is the difference between the NMI and INTR. First one is the characteristics of the NMI as follows. They are also known as the non-maskable types. Number 2 is that they are always give the higher priority over the interrupt. So first one is the non-maskable, second one is the higher priorities. Interrupt is the edge trigger, especially to the low to high transition. In order to the function, they must remain high at least for 2 clock cycles. This interrupt do not send out any form of acknowledgement. They do not give you any form of acknowledgement. Now, these are the characteristics of the INTR. Now, they are also known as the maskable type of interrupts. So this is the non-maskable type, it is the maskable type, it is a difference. They have the lower priority compared to NMI. Here is the higher priority, here is the lower priority. It is a difference. These interrupts are the level trigger, not the edge trigger. This is the level trigger and NMI use the edge trigger. And finally, this interrupt do not support the latching and must remain high till CPU acknowledge them to do so. So these are the difference between the NMI and INTR. So this is all about the interrupt of 8086 microprocessor. The next slide, I'm starting with the interfacing of 8086 with memory. Memory interfacing. Memory interfacing, if you want to try to interface the memory with the 8086, now question will ask why you need for the interfacing the memory. Because the memory, some data is stored in the memory. I want to take the data to the processor. I want to store the data in the processor. So transferring the data between the processor and the memory interfacing is needed. So for this case, 3 buses are taken very, very important role. One is known as the address bus, one is known as a data bus, and one is known as a control bus. Address bus's function is that to locate the memory location from where you can take the data and to where you can store the data. data bus carrying the data, and control bus give the direction to flow of the data, either flow towards the processor or away from the processor. So control signals, their read and write comes into the action. So interfacing the RAM, ROM, EEPROM to 8086, the general procedure of the static memory interfacing with 8086. The arrange the available memory chips. So do often 16-bit data bus fit. The upper 8-bit bank is called the odd address memory bank, and lower 8-bit bank is called the even address memory bank. So data bus is connected with the even and odd address memory bank, lower 8-bit, that means the D0 to D7 for the even, and upper 8-bit D8 to D15 for the odd memory bank. Connect available memory address line of memory chips with those of the microprocessor, and also connect the control signals RT and WR input to corresponding processor's control signal. Number 1, connect the 16-bit data bus of the memory bank with that of the 8086 microprocessor. The remaining address line of the microprocessor BHE A0 used for the decoding and required chip select signals for the odd and even memory banks. CS of the memory derived from the output of the decoding circuits. Now I explain the memory interfacing with a problem. So in the problem it is written that interface with the memory, two 4K into 8 EEPROM and two 4K into RAM, select the suitable maps with chip 8086. So one EEPROM size is 4K into 8, so 2 it is nothing but the 8K into 8, similar over here. But what is the meaning of the into 8? Into 8 is nothing but it is indicating for the byte. So interfacing of the memory, I explained in here also, there is a buses are taking the important role. And first is the address bus. So selection of this chip, EEPROM and RAM to 8086 address bus is required. So how do we find the address bus? I explained everything in detail in 8085. So directly I come to the point. This is the 4K into 2. That's why it is written the 8K. So I'm taking the 2 to the power x, where x equals to number of address line required to interface a EEPROM with 8086 as well as the RAM of 8086. Why say a RAM? Because the size of the both the cases are same. So it is nothing but the 8K is nothing but the 2 to the power 3, and it is the 2 to the power 10. That's why 10 plus 3 13. So x become 13. So 13 address line and required to these two chips to interface with 8086. Now I'll explain the address table of that. So it is the address table. So address table, I'm taking a pointer. This is the A0 line, it is the A19 line. What is the difference between this address table and previous what I explained in the address table in the 8085? There is 8085 starting with the lower value 000 each, after that it incremented. Here is starting with a higher value, after that I decremented. So initially FFH is the starting value. I am writing the all the lines A0 to A line in the high, and the x is 13. So I'm 13 line becomes the 0 from the right to left. So this is the A0 to A12, and rest of the line I'm copying from the upper one and paste it over here. The next location address, so location address of this ROM is the FFFF AFH to FE000H. So this is the address. Now next address is that this previous address -1, we can get the FDFFH. I'm written FDFFH. Similarly 12 lines is high. I'm writing the 12 line is high over here, and rest of the line and copy to paste over here. Now same thing. Look at in this line A0. This is 10. This is 10. This is 10. This is 10. So this is the select same. So up to which it is same? Up to this it is same. Then there is a difference on the A13 line. After that, A15, 14 to A19, all are the same. So I'm segregating this first. I'm segregating this A13 line. Now, why question will coming if you segregate the A13 line and this segregated line taking as the input of the decoder? Sir, you have explained this thing in 8085 also. Now, why you segregating this A0 line? Because we know A0 and BH but combination of these is denoted which is the even and odd memory. That's why we are taking the A0. That means A1 to A12 line is added with the address line with the chip of EEPROM and RAM of A0 to A11. That means pin number of A0 to A11 of EEPROM and RAM that is connected with that A1 to A12 of the processor. So I'll explain in the next slide with the help of the diagram. What I told that is replicated over here. This is the ROM, this is the RAM. Two ROMs are there, each size 4K into 8. So this is the address line of the ROM 1, A0 to A11, it is A0 to 11. But in the microprocessor, A1 to A12 connected. Why I'm taking the A1 to A12? Because A0 is segregated for the choosing the even and odd. So it is the even is connected to the lower order address bus, lower order data bus, sorry, and odd is connected to the higher order data bus. So that's why I can identify it is the even and it is the odd one. So here MRD bar, memory read bar is connected over here. It is a control signal because the ROM is there. That's why write is not there. In this here, RAM 4K into 8 and this is the RAM 4K into 8. This is the control signal WR bar, RD bar is connected to the MRD bar, MWR bar, memory read write bar, and data bus is connected, lower order connected to the even, higher order connected to the odd, and this is nothing but the address lines are connected also over here. Now how can I select the chip? I select the chip with the help of this decoder. This decoder I am taking the A0 line which is segregated in the last slide and A13 line which also I mentioned there is changing in the A13 line, that is I taken as an input, and as also I taken the input of the BH bar. Now look at here, I'm taking a pointer to explain that thing. First I take a pointer. Now what will happen if there is the 3 inputs are there, obviously there is a 8 outputs are there, O0 to O7, and these outputs are the active low output. Now for the CS bar 0 and 2 connected, CS3 bar 0 and 1 connected to the CS4 bar, so this line is connected over here. So complexity of diagram we are not connected over here. Similarly CS1 bar 4 and 6 is connected, and CS2 bar 5 and 4 is connected. This is connected from the output of this line. So question is coming, why 8086? Obviously 8086 is there because this address line connected with the 8086, this data line connected with the 8086, this control line is connected with the 8086. So only the complexity of diagram I'm not putting over here. So this is all about the memory interfacing of 8086 microprocessor. So in this video lecture, I explained the interrupt of 8086 microprocessor followed by the memory mapping of the 8086 microprocessor or interfacing the memory with the RAM or EEPROM with 8086 microprocessor. So these are the references. So this is my contact details. Feel free to write me if you have any problem. So this is end of lecture 26. Meet you in lecture 27. If you like, please subscribe my YouTube channel. Thank you very much.